Okay, cool. So I hope you guys are all doing well. Your third exam is going to cover a lot of aldols, enolates, condensation reactions. And so I'm going to just walk us through a lot of those reactions and the mechanisms. So we'll go ahead and get started. And at any point, feel free to message in the chat for any of the leaders if you have any questions, or you can like unmute and ask as well. Okay. So you guys first started off this this exam content with alpha halogenation. And so we have a few reactions that we need to know for this. Starting off with the most basic, we could have an acid catalyzed. And so when we have these, we're going to be using a carbonyl, any sort of acid, and then your halogen. And so you will be halogenating the alpha position. So your final product will be adding a bromine to that alpha position. Okay. So then just like normal acid reactions or mechanisms, you're going to begin by protonating your carbonyl. Okay. And then you're going to come in with some other water to grab this and send those electrons up. Okay. Once you get there, you can go ahead and send these electrons back down to go ahead and grab your bromine. And then lastly, you'll deprotonate to get back to your final product. Okay. On the other side of that, you can also go ahead and do your base catalyzed reaction. And so in this case, instead of using your acid, you'll just do any base. So I'll use NaOH, MBr2. And that will go ahead and give you the same, or sorry, not the same product, because you'll brominate twice for each of the available hydrogens on that alpha position. Okay. So in this reaction, instead of protonating first, because you don't want any positive charges, you're going to grab that hydrogen on the alpha position and deprotonate. Once you do that, because you have more base in solution, you're going to also grab that other proton to do the same reaction. And then you can brominate once more. Okay. So those are the two most basic. And then if we keep on moving forward, we can go ahead and consider the haloform reaction. So in this case, you have the same reagents as the base catalyzed. But the key difference is that you will have this alpha methyl right here, which means that you have 3 available hydrogens to deprotonate. And so in this case, and we'll walk through the mechanism in one moment, but you're going to go ahead and kick it all off. And so you're going to end up with your carboxylic acid as your product. And then you also have a byproduct of the CBr3 group that you'll kick off. Finally, don't forget that for haloform, you will need that acid workup, as we'll see in the mechanism right now.
Can you move back up please. Just, yeah, there we go. Thank you. Sorry.
I can keep it up. Okay. So your haloform will be really similar to the base catalyzed. So most of the reaction is the same. So we'll start by deprotonating again, just like above. You can bring in your Br2 to brominate. And then you'll do this process again. Then one more time with that third hydrogen. Okay, so once you have deprotonated all of the available hydrogens on that alpha position, you'll get to this point. And so from here, I'm going to scroll down a little. From here, your next equivalent of base will still come in and attack, but now it's going to attack the carbonyl carbon, sending these electrons up onto your oxygen, which come down to kick off your leaving group, which is now that CBr3. Okay. So once that happens, you're going to be left with this carboxylic acid and your byproduct of minus CBr3. So key thing to remember is that this reaction does not stop right here, like you have not made your final product, because what you have is this superacidic proton on this carboxylic acid. And so your minus CBr3 is going to go ahead and grab that acidic proton and deprotonate to get you to your carboxylate and then your other byproduct. So from this step is when you would have to add your acid water to do your final workup. And so I'll add that in to protonate and get me to my final product. I'll leave this up for just a little bit longer, but the next reaction that you'll need to know in this section is the HVZ reaction. And I honestly could not tell you what it stands for. So that's fine. But in your HVZ reaction, your starting material will be a carboxylic acid. You'll be using PBr3, Br2, and then a water in your step 2. And then this guy will give you your carboxylic acid with the alpha bromine on the other side. Okay. I am going to scroll now. All right. So yeah, just as a key point for the HVZ reaction, you're going to be able to alpha brominate your carboxylic acid without losing the carboxylic hydrogen. So now let's take a look at the mechanism. PBr3, you guys have seen multiple times by now. So it will still do the same thing. Your carbonyl will attack and kick off the BR. And then once you get there, you have this complex. We have our acidic hydrogen on the carboxylic acid. So the Br minus that just got kicked off is going to grab that hydrogen and send those electrons up to neutralize the oxygen. Sorry, no, it's not going to grab that hydrogen just yet. It's going to just directly attack your carbonyl. And then that way we form this complex that will be more stable since it's got 6 members in it. And then we can just cyclize those electrons around. So this hydrogen will come off to break this leaving group out. And that will give you a double bonded oxygen right there with your Br hanging off. Your leaving group is the OPBr, and then you're also going to get HBr through that 6-membered intermediate. Okay. And then I'm going to take this guy and just rewrite him over here. So from here, we're going to protonate with that HBr. Okay, and then our equivalent of Br minus that just got kicked off as our leaving group is going to grab that alpha hydrogen, send those electrons up to neutralize your oxygen. And then again, you're going to send these electrons back down after you form this enol. In order to get that bromine position. And then now from here on out, we're trying to return back to our carboxylic acid because the entire point of having the HVZ reaction is to preserve that carboxylic acid. So from here, we've alpha brominated, but we want to get that acid back. So you're going to go ahead and enter with your water. So you'll go ahead and protonate your carbonyl. And then your water can come into attack. From here, you'll just deprotonate that water. And then Br is a good leaving group. So go ahead and send your electrons down to kick off that good leaving group. And then your last step would be to deprotonate that carbonyl to return to your carboxylic acid. Okay. And I'll pause here for you guys to continue writing it down. Are there any questions so far that you guys want to ask? Okay, cool. So the next section that you guys got into was enolate chemistry. So I'll give you guys just a few more seconds on this page. And we'll talk about enolates. So your enolate, just in general, is the nucleophile that you'll be using. And so whenever you have a nucleophile, a lot of the reactions that you can do There are like 4 main types that Falzone really likes and that you'll see quite a few problems of. And so you can use enolates primarily for alkylation reactions. So that's like when you're attacking an R group that has a good leaving group, like Br on it. And then you can attack epoxides. Which Falzone absolutely adores. Classically, you can attack carbonyls. And so those are the reactions that we're going to be focusing a lot of our time on. And then you can also attack alpha beta unsaturated carbonyls. So these are the ones that look like this, where you have that double bond in conjugation with your carbonyl. And then these ones we'll talk about have a specific name. They're going to be your Michael reaction. Okay. So with enolate chemistry, a lot of what you have to consider is the type of base that you'll use to form your enolate. So a good example is using KH versus LDA. So if I have a molecule that looks like this, or I have a methyl on one side, I'm going to be deprotonating the alpha position to that carbonyl. So my two options would to be either approaching from this side or from the side that the methyl is on. When we have KH, this is typically run at like about room temperature. Since KH is smaller and it's at a higher temperature, we're going to prefer our thermodynamic control. So that means that when I'm deprotonating, I'm going to end up with the product that gives me the enolate double bond on the more substituted side. So this will be my major product. And then my minor product would be the opposite. Okay. On the other hand, if we're using something like LDA, LDA is very bulky and it's also run at low temperatures. So for those two reasons, we would get our kinetic control, which means that in contrast to our KH base, the major product in this case would be the less substituted double bond. Whereas the minor product would be the more difficult to access, sterically hindered product. Okay. And we'll also talk about LDA a lot more as we go into the condensations. All right. And then one more aspect of enolates that we should consider is which atom acts as the nucleophile. So when we have our enolate, we can draw two resonance forms for it. So first we have this one where we just deprotonated on that alpha position, but we can also draw a resonance structure to send these electrons up into our oxygen. Okay, so from here, if we were to go ahead and attack an electrophile, then we would have this product versus this product. And so between these two, this left product would be more favored. And the biggest reason for that is because the carbon-oxygen double bond is stronger than your carbon-carbon double bond. And so you really want to preserve this carbonyl because it will give your product more stability. Okay. So that's why generally whenever we have our enolate chemistry, we're going to be attacking from that carbon instead of from the oxygen. All right. And then let's talk about how we form that enolate in the first place. So again, we have two options. We can either do it under acidic conditions, and these will be pretty similar to what we saw above at the alpha halogenation portion. But if we have a carbonyl under acid, we'll go ahead and form our enolate like here. And so in this case, we're going to start by protonating our carbonyl like usual. And then some water will go ahead and deprotonate. Okay. And then the other option is to do base catalyze. So very similar as well. Just go ahead and use a base instead to get your same product. But in this case, you'll go ahead and grab that alpha proton first. And then you can resonate this structure in order to protonate your carbonyl, or sorry, your alcohol. Okay, so that was like the intro to enolates portion. Was there a question that I needed to go back on? Or
For these two, which atom acts as a nucleophile. So if the one on the left was more favored as a nucleophile, would the one on the right be more favored as an electrophile?
no, so they are both technically nucleophiles, but during your reaction, if you're drawing a mechanism, you should be using the left resonance structure because it'll give you more stability in your product. So your carbon should be your nucleophile in this resonance structure. Does that make a little bit more sense?
Yes, thank you.
Okay, cool. Are there any other questions that you guys wanted me to stop on?
Could you just scroll down to the very last thing you just did real quick? Thank you.
Yeah, I'll pause here for a minute. Okay, so then the next section that you guys got into was the bulk of this exam, and these are your condensation reactions. So remember that condensation reactions, you're basically taking two smaller molecules and then combining them into one larger molecule. So you'll be seeing like two molecules come together and yeah, form your product. So again, we'll start off just by reviewing the types of bases that you have. So generally you can use your NaOH or like NaONe, things like this. And just some characteristics that you should keep in mind are that these bases are going to be a little bit weaker. And so they generally will give you about like a 50-50 percent change between your starting material and your enolate form. And so for that reason, they're very good for self-condensations so that you have a portion of your original molecule that you can go ahead and attack after forming your enolate. And then another key thing to note when you're using these ones, and we'll see it a little bit later as I go through some of the reactions, but you want to make sure that you use the base that matches your ester if you have like an ester in your starting material. And so the reason for this is that whenever you're using these bases, you can have those transesterification reactions that we talked about on a previous exam. And since you don't want to be changing the R group that you have in your starting material versus your product, you want to make sure that you match them correctly when you're undergoing these reactions. And then the other base that you'll see quite a bit of is LDA. So characteristics of LDA is that it is much stronger. And so this will give you about 99% of your enolate form. And for that reason, it's very good for mixed condensations because you want to push that reaction forward. So then now we'll start with your aldol reactions just to see a little bit about when you would use which base. So your first one is aldol, and we'll begin with a self-condensation. So during your self-condensation, you're going to be requiring 2 equivalents of your starting material. And since you're using 2 equivalents of the same starting material in solution, you want to use a weaker base like we just talked about. So I'll go ahead and use NaOH with water and heat. And then your final product will go ahead and look like this. Okay. So the mechanism for these will all start to look pretty similar. But to start off, you're going to form your enolate by deprotonating on the alpha position. And then since we used a weaker base, we're going to have about 50% of our enolate in solution, and then the other 50% will just be our original starting material, which we can go ahead and attack now. Once we get here, we'll protonate. And then at this step, we're going to, since we have heat, we're going to do our E1CB. So another equivalent of base will come in to deprotonate that alpha hydrogen. This gives us a negative charge, and then our E1CB step will go ahead and kick off our pore leaving group. And so that will allow you to eliminate that alcohol. Okay. On the other side, if we wanted to do a mixed condensation, this one will occur if we have 2 separate or 2 different starting materials that we're trying to combine together. So for example, we could have this molecule and we're trying to combine it with a slightly different molecule. In this case, since we want to push it all to our product, we're going to use a stronger base, so LDA. And then we will have our product that looks like this. And so for this reaction, we want to first consider which molecule is going to act as our enolate. And so if I denote this one as A, and then we'll call this one B for right now. For A to be the enolate, LDA would deprotonate that alpha hydrogen again. And so we would be left with this molecule. And then looking at B, we would do the same process. To get to that enolate. And so if I were to say that A is acting on our enolate, and we're going to be attacking a normal molecule of B, you would see that this enolate will combine with your starting material. And then that will go ahead to form a combined product of your A on this side, and then it attacked your B portion right here. So that's how those two stitch together. And then you can also do the opposite version where B is attacking your A. And so if B is acting as your enolate to attack a normal molecule of A, then your product would just be a little bit flipped. And it would look like this. So between these two possibilities, now you want to consider which one would be your major product. And so the major product that you have is going to be this top one. And the reason for this is if you look at a normal molecule right here, this enolate has to go ahead and come down to attack that carbonyl position, but it's quite sterically hindered. Like you have these methyl groups around it, and then you also have that phenyl, which is all in the way. And so due to the steric hindrance of trying to attack that more substituted position, your reaction isn't going to proceed too far. So this one, you want to keep in mind to use the enolate that has the more substituents. Okay. So it usually comes down to a sterics argument.
Is being conjugated also a reason why it's the major product?
Yeah, that could play a role as well, because you would have that carbonyl next to your phenyl group instead of being destroyed. Yep, that's a good point.
Sorry, why was it again that the major product is major product?
Yeah, so in this case, you're using the enolate that's more subbed. And so when it attacks your electrophile, it has the room to attack that carbonyl position. If we look at this second row, that phenyl group is really, really large. Those methyl groups are also in the way. So it's going to be really hard for your enolate to get close enough to that carbonyl carbon in order to form that new bond.
Okay, so it's basically like because of hindrance.
Yeah, exactly, steric.
Cool beans. Okay, cool, thank you.
Molly, also for the last green product, the phenyl group should be on the same carbon as the alcohol.
Yeah, sorry, I did move that. Cool. Let me just jot down 2.
If we added heat at the end, would you get the double bond, or is that just not gonna happen?
If you added heat on the end, you would, but it would not be the conjugated double bond because this carbon already has 4 substituents. So if you added heat,
Oh, I didn't even realize that. Okay, yeah, that makes sense.
yeah, so it wouldn't be quite as favorable as like your normal elimination because it's not conjugated, but it's possible. Cool. Any other questions here? Okay, cool. Yeah. All right, then after those aldol condensations, you can go ahead and the next one that you guys covered was going to be the Claisen condensation. And so for this reaction, we're going to have 2 esters. In this case, since I'm using the same one, I want to use a base and it has to match the ester that I currently have. So I'm going to be using NaOET and ETOH. If I had a methyl, then I would go ahead and use that corresponding base. And then I'll have a workup at the end. And for these ones, they'll go ahead and stitch together as well. Okay. So same starting mechanism as usual. We'll go ahead and deprotonate that alpha position. And then attack the other equivalent. When I attack this equivalent, I'm going to go ahead and kick off my leaving group as well. So once I get to this step, I'm not done. I do have this acidic hydrogen right in the middle, and I have some negatively charged base that's lying around in solution. So the base is going to deprotonate that acidic position to give me another form. Okay, and so that's why I needed my second step to be an acid workup. So we'll go ahead and protonate that. And that will give me my final product.
Couldn't you just assume that the ethanol will get deprotonated? Why do you have to have that acid workup?
So if you have it that way, you're going to be going back and forth and it'll have an equilibrium. And so you would end up with pretty much like half of it being the deprotonated form and like about half of it being the protonated form. So in order to push it all the way to completion, you need to add that second step with the acid quench.
Perfect, thank you.
Yep. All right. So then the next reaction that you guys learned about was very similar to the one above. It's just the intramolecular one. So this is called your Dieckmann condensation. And it's just an intramolecular Claisen. I'm pretty sure Falzone makes a joke about this one, but yeah. When you're here, you're gonna have your esters. 1, 2, 3, 4, 5, 6. And you're gonna be able to use NaOMe. Notice that I'm matching the base. Cannot emphasize how important that is. And then your acid quench. And in this case, you're doing pretty much the same reaction that I just showed, but instead, since it's all one molecule, it's gonna be intramolecular, so you'll form a 6-membered ring. And then I'll also be showing you the decarboxylation reaction, like kind of combined in here. Okay, so we'll start off with this. Your base is going to come in to deprotonate your alpha position to get to that enolate. Also, if I drop a carbon at any point, someone please just point it out. All right, once you form that, you're going to go ahead and do your intramolecular attack on that other carbonyl to form your 6-membered ring. Like that. And I'm pretty sure I counted this right. Pro tip, number your carbons like all the time. Oh, that's not going to be correct. Yeah, cool. All right, and then we also kicked off our base as a leaving group. And so again, we're going to deprotonate that acidic position. And so we get to this intermediate. Once we get here, we're going to do our acid workup. So I will be doing this part in a couple steps just so that you guys can visualize it. But how it would actually happen, like if you were to do this in the lab, all of it would happen at once. So I'm first going to protonate that acidic position. And then since we're adding acid water, it'll go ahead and convert my ester back into my carboxylic acid. So I'm not going to show this mechanism because you saw it on the last exam. If you forgot about it, I would recommend going back to the last exam to take a look at it. But this is just under acid water. Okay. And then at this step, since we're doing it under heat, we're going to do our decarboxylation reaction. So in this mechanism, I'm going to redraw the molecule just to make it a little bit larger. But we have this 6-membered ring kind of intermediate right here. And so what will happen is that these electrons in your carbonyl will come out to grab your hydrogen. These will break out and cyclize around. After those electrons move around, we'll end up with this intermediate plus a CO2 byproduct. And then once we get here, we're going to just detautomerize back to our more stable keto form. Okay. So all of this just happened in the H3O plus and heat step, which is why your final product will just be this carbonyl, and you'll have the CO2 byproduct and then also the base byproduct that we created earlier at this step. Okay. Just some more notes about the decarboxylation reaction. Your decarboxylation reaction will pretty much happen whenever you have acid and heat, as long as you have an alpha carbonyl to the carboxylic acid. So whenever they're just right next to each other, so if you have your carbonyl right here and then it's alpha to the carboxylic acid position, you can form the 6-membered intermediate and it'll automatically happen. And then just remember that your keto form is always more stable, so it'll always tautomerize to, yes, that reaction. Okay, I'm gonna pause here once more, just so that you guys can jot those down. If there's any questions, feel free to speak up. I know that the chat is going right now, but that's fine.
Is there an OH like at that elbow with the ester coming off the ring?
Are you talking about like right here?
No, here. Oh, I can't annotate. That's okay. It's all good. So like there's like the 6-member ring and off of carbon 1, is that an OH coming off of it?
No, sorry, that's an H with a terribly drawn arrow.
Okay, okay.
Yeah, so it's just deprotonated. Yeah. Cool. All right, I'm gonna keep on moving forward. So the next reaction that you guys covered is the Novanagle condensation. Novanagle. Okay. And then this one is going to be your 1,3. Hello. So it's pretty much your aldol, but the key part is that you have a 1,3 dicarbonyl as one of your starting materials. And so the 1,3 dicarbonyl is going to look like this. The naming occurs because of those 3 carbons. And then you can add whatever other carbonyl you want to attack. In this case, I'm going to match my base again. And I'll be doing it under heat. Sorry, I didn't mean to scroll. So that I will deprotonate at the, eliminate at the end. And I'll show you that mechanism. All right, so that's just like a general reaction. And now we'll take a look at the mechanism. So similar to all of the ones that we've already seen. Your base will deprotonate. You'll go ahead and attack that next carbonyl. And then you'll protonate this one. Okay. And then, sorry, I'm actually going to redraw this with a little bit more space. So because we created this OET, like we saw before, it'll come back to grab that acidic proton. And then here is where you'll have that E1CB again. So after that acidic proton is deprotonated, we'll have that negative charge, and then it'll come down to kick off your pore leaving group. And that's where you'll get your final product. I'm gonna add a little bit of an adjustment. So another reaction or like synthesis problem that might be very common is that you'll see after you get to this product, he'll go ahead and add just an acid quench under heat. And so this will go ahead and convert all of your esters into carboxylic acids using that decarb step that we did like just above right here. And then once you have that decarb, you'll end up with a different product that looks like this. So that's pretty common. I would say if you want to see some examples, there are from the problem set and also definitely on the back test too. Okay, I'll pause here to give you guys a little bit more time to copy it down. If there's any questions. Yeah. Okay. So then the next reaction that you guys saw was the Michael reaction. And in this case, you're using an enolate on an alpha beta unsaturated. So as a general statement, you're going to be using an enolate on the alpha beta unsaturated carbonyl. And then this gives a product that's a 1,5 dicarbonyl. So if you're working on a synthesis problem or any of the first page problems and you see a 1,5 dicarbonyl as your product, this would probably be my first go-to to see if it works. Okay. So we have our enolate and then the alpha beta unsaturated carbonyl. I'll draw in a second. So first we're gonna use our base. And that will form our enolate on that alpha position. And then the alpha beta unsaturated carbonyl is any variation on this molecule. And then lastly, you'll want to have an acid workup with heat. And then your final product will look like this. And these are the positions where you have your 1,5 dicarbonyl. Okay. So I'll walk you through the mechanism once more. Your base attacks at that acidic proton. From here, you'll go ahead and attack your alpha beta unsaturated. So all of those electrons will shift over. To give you this intermediate. Okay. So from here, you'll have some base in solution. So you can go ahead and send these electrons down to reprotonate. And then from this, we're going to do that third step with the acid quench. And from your acid quench, you're going to replace all of your esters with carbonyls. Sorry, not carbonyls, carboxylic acids. And then your decarboxylation will automatically happen right here with that 6-membered intermediate. And that is how we would end up with our final product looking like that. Okay. So very similar to the other reactions that we've walked through.
I have a question.
Mhm.
So in this example, is the H3O plus only used to hydrolyze the esters? Like, is there a deprotonation that happens because it's 1,3 dicarbonyl?
Wait, sorry, could you ask that once more?
Is the H3O plus only used to decarb or to hydrolyze the esters, or is it used because like it's gonna be deprotonated between the two esters?
Yeah, so I think I understand your question, but any of the other leaders can like completely jump in and correct me if I did not answer this. But the H3O plus can be used at this step as well, because it'll do the same thing. And all of those will just happen together. The H3O plus does do, like the primary part that I put into this mechanism was so that it would convert your esters into carboxylic acids. Do any of the other leaders want to like add on? Slash, did that answer your question at all?
Yeah, thank you.
Okay. All right, cool. Any other questions? All right, then we'll keep on going forward. So then the next reaction that we have is the Robinson annulation. And the Robinson annulation really just combines two of the reactions that we've already gone through. So it is really just a Michael plus an aldol, or a Michael plus your Dieckmann, which is just your intramolecular Claisen reaction. So as an example, we can have our alpha beta unsaturated and then your ester. So this is the portion that's your Michael reagents kind of, yeah. And then you have your base with heat. And so we'll go ahead and draw out the products that we'll get. In this case, we'll actually get two products, and I'll show you the mechanisms onto how, as to how to get each version. So to start off, like I said, it's going to be identical to your Michael mechanism. So your base comes in to deprotonate. At your alpha position, that will come out to attack your alpha beta unsaturated carbonyl. One, two, three, four. Right here. And then in this circumstance, we're not doing an acid quench, so you should be using the protonated version of your base to protonate right here in this step. So that will give you this intermediate. From this step, we want to do your aldol. This one will be more of a Dieckmann because it's intramolecular. So your another equivalent of your base is going to come in to deprotonate. The reason why I'm choosing this end is because my goal is to form that 6-membered ring. So if I'm attacking this carbonyl, counting down, using the last carbon will give me my 6-membered ring. And so that's the one that will be more likely to get deprotonated. And so these electrons will come up to attack that carbonyl position. I'll number the carbons again. All right, and then from this, you're going to go ahead and protonate again. Okay, and then now, since we have heat, we're gonna go ahead and do our elimination step. So you're going to have alpha protons on both sides. So you can either get it from this one, or the other option is from the other side. As in that hydrogen right there. So I'll do the purple one first, and then I'll go back and do the blue one. But your base will come ahead to grab this proton. And then you'll have your E1CB elimination, where these electrons come down to kick off your poor leaving group. And then in my blue one, it's the same mechanism, where you go ahead and deprotonate first. And then your E1CB elimination occurs. Okay. And so that's how you get your two different products for this example. A few key characteristics of your product for your Robinson annulation. Something that you should keep in mind is that generally you'll form these 6-membered rings. And in these 6-membered rings, you'll probably have one double bond. Usually the double bond will be conjugated, so you'll see it as an alpha beta unsaturated carbonyl. So in this case, you would have like your alpha beta unsaturated portion right here. And then in this portion, you would also have it right here. So those are just like a few characteristics that if you see on a synthesis problem where you're forming a 6-membered ring with the alpha beta unsaturated carbonyl in your product, then you probably have undergone a Robinson annulation. Okay. And then I think I just saw one question, which was like, which is more favored? Since both of these are conjugated, they're pretty stable. My vote would be for the purple one just because it's less sterically hindered, but ETO- isn't super big either. Does anyone else want to weigh in on this?
Would the one on the right be more favored because it's more substituted?
Yeah, that's
Or
a good.
is-
Yep, I didn't notice
Or
that.
does that make it more hindered though?
I feel like it depends on the temperature.
So since it's being heated, it would be a thermal control. So the one on the right could be your more stable product. Yeah, because this part, since you're doing an elimination, you're going to be under heat. So you would probably want your thermal control, which would be this blue one. Okay. Any other questions on this? I'll hang out here for a second. So we decided that the blue one is going to be your major product because you're heating it. And so whenever you're under heat, you're going to go with your your thermodynamic product. And so that one would be looking at which double bond is more substituted. So in this blue one, it has 4 substituents, whereas in the purple one, it has 3. And so the blue one should be more stable as a thermodynamic product. Okay, there's another question. Okay, yes. Generally, you'll see it inside the ring just because it is more substituted. Oh, I understand. Are you talking about using this methyl position? Sorry, this hydrogen position right here?
Yeah, that's what I meant.
Okay, yeah. It's less likely to occur as well because it wouldn't be conjugated in that position. So I'm just gonna sketch out like what that would look like. It would be like this. And so you'll see in that position, you wouldn't be creating an alpha beta unsaturated carbonyl, so you would have no benefit of conjugation to stabilize your product. Okay, cool. I am going to just like erase it. Yeah. All right, any other questions? Okay, then we'll keep going. So we're switching just a little bit, but now we're going to talk about your malonic ester synthesis. Okay, so your malonic ester just looks like this molecule. And then you'll be using a matching base. And then in this case, we're going to do an alkylation. So we'll be attacking an R group attached to a good leaving group, such as Br, and then your acid quench. And then the product that you'll form after this is a carboxylic acid combined with that R group. For the mechanism, we'll deprotonate at that acidic position. And then we'll bring in this R group to attack and then kick off the good leaving group. Okay. And then from here, we're going to bring in that acid quench. And so when we have this acidic conditions, we're going to turn those esters into carboxylic acids. And then we're also going to have heat. So it'll do the decarboxylation reaction all in one step. I'll draw it out again, just in case you guys haven't seen it. But yeah, once we get here, your carboxylic acid is adjacent to another carbonyl. So then this heat will go ahead and decarboxylate the reaction, the molecule. All right. And then the next couple of reactions, I don't think have been on the problem sets as frequently as the previous ones. So I'll go ahead and walk through them. But we have the storic enamine synthesis. Okay, so in this case, we're going to be using our enamine. And then we'll be attacking an alpha beta unsaturated carbonyl, and then an acid quench. Okay, and then our product will go ahead and look like this.
Excuse me, could you go just a tiny bit slower?
Yeah, do you need
Thank you.
an older one?
Yeah, thank you.
Yeah, I'll pause. Sorry, guys. I talk really fast when I'm like nervous. So if you need to see anything, I can scroll back up.
We'll also post the recording of this, and if you ever want to like go back to a part, you can always just like zip back.
Okay. Yeah, does anyone want me to scroll to an earlier reaction? Okay, that's chill. I really don't mind. You guys can tell me to stop whenever. Okay, so I'll walk through this mechanism. So we'll start with our enamine, which you guys should know how to form from exam 1 reactions, I think. And this will go ahead and attack our alpha beta unsaturated. So the lone pair on nitrogen comes down, sends this double bond electron out to attack that beta position, and then these electrons will get pushed up to our more electronegative oxygen. Okay, so those two pieces get stitched together. From here, we're just gonna do like a few protonation. So those electrons will come down to get protonated to give us this intermediate. Okay. Since our nitrogen is still positively charged, we're going to attack with water to send those electrons back up. Okay. And then from here, we have like an idea of where we want this mechanism to go. So we know that our product is going to be that 1,5-dicarbonyl with that carbon, so with the enamine replaced as a carbonyl. So now our goal is to shift around protons so that we can make this nitrogen group a good leaving group so that we can kick it off. So from here, we're going to do a bit of a proton transfer. So that nitrogen group is going to be positively charged. And once it's positively charged, it becomes a good leaving group. So our electrons on oxygen are going to come down to kick off that nitrogen. Giving that secondary amine as our byproduct. And then the last step will just be water to come in and deprotonate. Okay. I'll pause there in case you're still writing, but are there any questions on this one? Okay. All right. Like maybe 5 more seconds. Okay. All right. Then the next reaction, I think you guys just recently covered in lecture. It's going to be your Gabriel synthesis. Right. And so in this reaction, we're going to start with this molecule. And this is your imide. Yeah, imide. And using base, some R group with a good leaving group. So whichever carbon chain you want to add, and then also an acid quench. And then this reaction will go ahead and give you your primary amine with that R group that you had added during the reaction. And then your byproduct is this thing, which is called your diacid. Okay. All right, so this mechanism is kind of bulky. So I'll like write and then I'll pause because I'm gonna have to scroll in between. So just like let me know if you want me to slow down at all. But we'll start off with our imide. Okay, and then like usual, when we're operating on basic conditions, we're gonna deprotonate. And then once we have that deprotonated, we're going to go ahead and attack that R group to kick off bromine. Okay, so now that we have that added, we'll introduce our acid water in order to get that primary amine freed from the rest of the molecule. So from here, we're gonna add in acid water. First step, whenever you have that acidic condition, is to protonate your carbonyl. Because that's protonated, we'll come in with some water to attack the carbonyl carbon. All right, and then remember that we're trying to free this nitrogen group. So we're gonna do a series of proton transfers in order to make it a better leaving group to kick it off. So first, right here, we're gonna do a proton transfer to switch that proton over to the nitrogen.
With proton transfers, the reagents are like the base and acid water, or
I can draw it out. Yeah, generally it probably would happen in 2 steps. So first some water would come in to deprotonate right here. And then next, because you just protonated that water, which is why you're under acidic conditions, this nitrogen would grab it and then give you like this product right there.
thank you.
Mhm. Okay. Cool. And then once you're here, you'll go ahead and use your lone pair on oxygen to reform a double bond and then kick open this leaving group. So the product that you would get would look like that. Okay. And then water comes in to deprotonate there. I'm gonna leave it here for a second because I'm gonna have to scroll down. But what you'll notice after this water step is that we've pretty much gotten the top half of our diacid. So we have this first top carboxylic acid. And so what I'm gonna do next is just repeat that entire mechanism with the water in order to make the same thing on the bottom. Also, I realized that this should have been a carboxylic acid. Yeah. Okay, I'm gonna scroll down a little bit unless someone yells at me to not.
Which one did you say was supposed to be a carboxylic acid? I missed that one.
It was right here in the product. There's
Okay,
supposed to be two acids, like that's where the name comes from. Diacid means two carboxylic acids.
okay, thank you.
Okay, I'm gonna move this down a little. So after that water deprotonation step, I have my carboxylic acid on the top half. And now my goal is to do the same thing to the bottom half. Okay, so I'm going to come in with some more acid water. It's going to go ahead and protonate. From here, water will come into attack again. And then the same proton transfer that is shown in blue, that same mechanism will happen once more. So I am not going to write it fully out because it's identical to what's above. Okay. Once we get here, that nitrogen is positively charged again, and so that makes it a good leaving group. So I'm going to swing some electrons down to kick it open. Okay. And so that is how I got my primary product, which is that primary amine. And then for completeness, this guy would also just get deprotonated with water. Which gives me that diacid that I was referring to above. Cool, so I'll wait here for a little bit. Okay. Are there any questions that people want to bring up? All right, I'll give you guys just a couple more seconds on here. Okay. And then the last reaction that I have to share with all of you guys is going to be the azide synthesis. And that is just when we start with some primary halogen, and then we add NaN3, which is your, I'm pretty sure this is the azide, and then you'll add in H2PDC. Okay. And then the product that you get out of this is your primary amine again. So the mechanism for this one, we have your primary halogen. NaN3 is really just negatively charged nitrogen. So this will come in to attack that R group and then kick off the Br. And so you'll form this intermediate. N3 has a bunch of resonance structures, so this can also be drawn as this, which is just where the electrons right here swung over. Sorry, the other way. Not the other way. Yes, the other way. So the lone pair on this N nitrogen came down to form the triple bond, and then these electrons came over. All right. And then once you get here, all you have to do is apply H2PDC, and that will give you your primary amine. Okay. Any questions on this reaction?
Do we know how it does that, or do we just trust that?
You can trust it. H2PDC operates by a bunch of radical reactions. And so they're all like the fish hook reactions that we did like either very late Orgo 1 or very early this semester, but you don't need to know the exact mechanism for those ones. Okay. Any other concepts that you guys want to go over a little bit more? Hi, dog. Okay, cool. Well, that is all of the content that we were hoping to cover during this review session. So if you guys don't have any questions, like that was the bulk of what you'll see. We're gonna start doing a few practice problems that I think Juan will take over to do. Yeah. But otherwise, like, thank you all for coming. And I put Juan on the spot, so he'll take a second to get set up.
Yeah, you really did. That's
Yeah, I
fine.
did.
All right. Yeah. All right. Thanks, Molly. Everyone give Molly a little Zoom round of applause for doing a great job. And now we're going to go and transition over onto some problems which are coming out of my problem set that I sent you guys a couple weeks back. I will be sending out a problem, an answer key later on, so stay tuned for that. Okay, so this first problem that I'm going to be doing is problem number 23, part D for my problem set. And I sent these out if you are in Learning Den. So if you're not in Learning Den and you don't have this problem set, I can send that out to you if you want. Okay, so, or we can get that out to you as well. All right, so for this one, 23D is just asking you to predict the product. And then a couple things that you want to note here is that you're going to have an aldehyde, you're going to have an alpha beta unsaturated ketone, and then you're going to have some sodium methoxide and methanol present in there. Okay, the big thing that's determining whether or not your reaction is going to go directly to completion is going to be the heat that you have over here. Okay, so the way that we're going to do this okay, so this is basically going to be Robinson annulation. Remember that your Robinson annulation is just divided into your Michael and then your aldol after, as Molly just showed you. Okay, so remember to kind of just recap that, you can go in and take your base, your sodium methoxide in this case, That rhymes. And then you can go and end up with your enolate. All right. Then after you have that, the next step would be to go in and add your alpha beta unsaturated carbonyl. Which ends up giving you a product that looks like this, a very diagnostic 1,5 dicarbonyl-like product. Okay, then afterwards, you go and then reform the carbonyl, and then you're going to quench your product in order to end up with your final 1,5 dicarbonyl, which is part of your Michael. Okay, but remember that here we have heat. So the heat is actually going to allow this to not just stop at Michael, but to keep going and doing the full Robinson annulation. So the next step, as we mentioned, would be your aldol. All right, and then in order to go ahead and then do your aldol, you deprotonate over here, and what was it that Molly said that makes that proton very acidic? Anyone remember?
The stability caused by the product of like the cyclic ring.
Very good. Yep. So from here you could form a 6-membered ring, which we're going to go ahead and then do. Helps the number 1, 2, 3, 4, 5, 6. Then we can go reform the carbonyl, attack this guy. And then you end up with this, essentially what is a deprotonated aldol. Then afterwards, you end up with the aldol. So this is essentially what your aldol is. But we're going to go ahead and then continue to dehydrate it afterwards. Let me move this a little more down. And the way that we can dehydrate that aldol is, as we saw earlier, to do an E1CB. Now I've noticed that when I've graded exams in the past, people kind of just go and then do the straight up E2, which is wrong. You're going to lose points for that because remember, alcohol is a poor leaving group. You can also form a pretty stable anion, which in this case is your enolate. Form carbonyl, you form your alpha beta unsaturated carbonyl. Then you end up with your final alpha beta unsaturated carbonyl product. Oh yeah, so the product of this reaction, I'll just write it again up here, is this. I will scroll back down. All right, any questions on this? Cool, so this is just your average Robinson annulation. Notice, I mean, me being experienced with this, I probably can draw out the product without doing the mechanism, but that's more of me just like flexing on you guys and not a suggestion, okay? The real thing is that for a lot of these problems, unlike what you've seen before, it might be quite difficult if you just try and predict the product without drawing the mechanism. For doing a reaction like osmolysis or BH3, of course, you didn't need to draw the mechanism to understand what was going on. But for Robinson, you might lose track of a lot of things if you don't actually draw the mechanism. So go ahead, draw the mechanism, take time on the exam. So that way you can make sure that you know what's going on without eating up a carbon. And especially with this topic, it's really easy to miss or add an extra carbon. Happens to me all the time. I've done this for like 40 years now. Okay, so now let's go ahead and move on to another problem. This next problem I'm going to be doing is problem number 14 on my problem set. If you guys want to follow along. Molly, can you actually do me a favor? Do you mind just posting the do you mind posting the problem set in the chat for like all those people who don't have the problem?
Yeah, I got you.
Wait, could you scroll back up like for a sec?
Sorry, what was that?
Can you scroll back up,
Yes.
please?
Yeah, I'm scrolling. My Wi-Fi kind of sucks. I'm sorry. There you go.
Thank you.
Yeah, in the future, guys, I know I stopped earlier and I asked you guys have any questions on this. During that time, you can use that to like ask me to stay here longer, but you know, it's a bit inconvenient for a lot of people if I scroll down and then scroll back up. So just that way, if you need me to stay on, you could take a screenshot if you want, I don't care, or just ask me to stay a little bit longer. Okay, so now let's go ahead and move on to problem number 14. And the text of this problem, I'm not going to write it all out, but it says, why do you think that this bottom reaction is likely to undergo self-condensation as opposed to this top reaction? Okay, so if you understand, or actually, I mean, I already gave you the products for this within the prompt of the question. So the reason why the bottom reaction is less likely to undergo self-condensation than the top all boils down to pKa. So when we're thinking about what we're dealing with here, this proton is going to be less acidic than the proton here on the bottom, right? That bottom proton has a lower pKa. You don't need a pKa chart to look at that. You just know based off of the fact that you have a more conjugated system, okay? So as a result, that means that when you go ahead and then you form the product, or like you deprotonate to go and then form the product, then you go and then you, I guess like before the self-condensation even, let me just redraw this. Yeah, here we go, I got it. Move this down here to show just the first deprotonation step. But when you do that, so you end up with this enolate, and you end up with this enolate. Okay, now looking at comparing these two reactions, right? We actually end up seeing that this base or this conjugate base is more stable than this conjugate base, right? Because here we have a 5-atom conjugated pi system, whereas up here we have a 3-atom conjugated pi system. Cool. So that means that this bottom reaction over here is more likely to favor the products, or rather the products are more favored. Okay, so as a result, the bottom reaction has a greater KEQ equilibrium constant. So more enolate can be formed. Which means that you have less starting material to condense on. Cool. So let me kind of just like put these closer together so you guys can see. Are there any questions on this? Actually, I'll leave it like this.
So the top one is more likely to perform self-condensation.
Yeah, that's right. And that's just because the top one, you still have that 50-50 mixture because that proton is acidic, but not nearly as acidic as the proton that's in the bottom reaction. All right, the next one, or do you guys need this? I'll leave this up for like a couple more seconds before I scroll down. All right. Next one I wanted to go over. There's two more problems that I want to go over. Next one is going to be problem number 25. And this is going to be 25A, so just the first one. And then this is one of those retro Robinson annulation type problems. Okay, so it's asking for the starting carbonyl problems for the following Robinson annulation products. So remember that when you're doing a Robinson annulation, again, it boils down to your Michael followed by your aldol. So that means that the aldol was the last step. Now you know that when you did the aldol reaction, the last thing you did was form that new bond between your alpha and beta carbons. Okay, so we can go and then break that to see what the last intermediate was. And then you end up with this, which is a Michael product. Okay, so now from this, there's actually two possible ways that you can go about this one. Either one is fine, either one would lead you to that same product. But if you went and decided like what your starting enolates could be, you can either go and then cut over here. And by cutting over here, you would end up seeing that it would be alpha and beta to these guys. This would be your alpha beta. So that means that everything that was over here would be part of the enolate or part of the nucleophile. Okay. And that means that the alpha beta unsaturated carbonyl that you formed was this one over here. Yeah. Okay, so and this is just one of your possibilities for what you could have done here. If you wanted, you could have also gone ahead and then cut right over here, which is alpha and beta to your other carbonyl. So that means that this part over here would have been part of your starting material. Okay, and then that would have given you. Let me see something real quick. I think am I missing a carbon? Yes, I am. I'm missing a carbon right over here. There you go. Or am I? Oh wait, no, I'm good. 1, 2, 3. I think I should be fine. Yeah, I don't think I'm missing a carbon. So yeah, I have this, and then for the other one, I mean that my starting enolate would have been this guy. Or that would have been like the starting material that I would have used to form my enolate. And then I would have gone and formed, and this would be my alpha beta unsaturated. Also, assuming I have, let me see, because I have, here, let me, it will just have by numbered. We call this 1, 2, 3, 4, 5, 6. Then I have 1, 5, 6, 4, 3, 2, 1. Okay, yeah, we're good. All right, yeah, and then that just means that this would have been my carbon number 6. This would have been my number 5, 4, 3, 2, 1. And then this would have been my 1, 2, 3. And then this would be 4, 5, and 6. Cool. So if you try drawing a Robinson annulation for either of those starting materials, then you would be getting to that product. Cool. It's not every case when you do Robinson annulation that you're going to have 2 possible sets of starting materials, but in this particular case, it would work out. Cool. Any questions on this?
All right,
So
when
the-
you break the, oh, go ahead.
Yeah, sorry, I just wanted to note that Alice pointed out that the methyl group should be in the alpha position if you want it to match the problem set, but it's just same process no matter where the methyl group is. So think about it as an extra practice problem.
Yeah, but Juan's answer right here is correct for the starting material that he drew, but you're right that it's not identical to the set. But yeah, more practice, always good.
Yeah, I was like, because I was so confused. I was like, wait, I knew this, like, I knew my, when I was writing this up, it would be different. So yeah, the one thing that you would have to note though is over here, if you want to form the enolate, you need to form this enolate from KH. Cool. Yeah, you need to form the enolate with KH because you want it to go and then form at this position right here at carbon number 5. All right, any other questions?
Where you broke the bond, like in the long one, does it always come like after the alpha carbon?
So yeah, you always make the new bond that you make with any enolate is between the alpha and beta carbon.
Okay.
All right, are we ready to move on? All right, and then for the last one, I wanted to go over one of the syntheses, which I hopefully will write down properly this time, and that will be number 12. And then that synthesis looks like this. All right, so any ideas on how to potentially go about doing this?
I tried to do this problem. I think what I did was wrong. But I thought that you could do you could use like a Lewis acid if you work backwards, and then if you had an acid chloride. So I thought you could make the ester into an acid chloride. like going through a carboxylic acid.
Okay, so make the ester into an acid chloride. So first, hydrolyze it. And make it into an acid chloride. All right, then what?
I thought you could use a Lewis acid to attack like a.
So like AlCl3 and then water like this.
Yeah, that's what I was thinking.
Okay, so there is something wrong here. So the chemistry looks fine, but something in here is making your life a little harder. Anyone want to guess what's making your life a little harder here?
I think it's the double bond.
The double bond. And what's going on with the double bond?
If I don't think it would be in the correct place.
It wouldn't allow rotation.
Very good. Double bonds don't have free rotation. So then this is going to be a cis double bond, sorry, a trans double bond. And the product has a cis double bond. You can't just magically like rotate that double bond to make the ring. So we actually have to do a bit of a workaround. So what do you think we should do? I guess before we even hydrolyze the ester, what do you think we should do?
Do H2 PDC.
Yep, H2 PDC to just get rid of it. We can make it again later. Okay, and then that we'll get rid of that double bond. So that means you don't have the double bond in the next step either. And we can go ahead and then hydrolyze and then make the acid chloride. All right, now in the next step, I agree. Now that you don't have that double bond, you can now make the ring. And then that's just with aluminum trichloride and water. And now we need to go in and get that double bond there somehow. Any ideas?
You could do a benzoic bromination and eliminate.
Yep, so you could do benzoic and eliminate. Or instead of benzoic bromination, you can also do acid catalyzed bromination as well. So maybe instead of doing it at that alpha position to the benzene ring, you could do Br2 and some acid like acetic acid or acid water. That doesn't matter. Okay, the only difference would be a regioisomer, where this one would end up giving you this guy, and then this one would end up giving you this guy.
Why do you use ACOH?
It's an acid.
Okay.
Like I said, acid water works here too. Cool. Yeah. So then the regioisomer will be different, but you eliminate to get the same double bond. Cool. Any questions about this or any other methods that you guys might have chosen to do this? All right, well, that was just a bit of a sneak preview of the problem set if you haven't worked on it yet, except for this one. This one was just whatever. But yeah, so hopefully this all made sense to you. And yeah, if you have any other questions about the problem set, remember there will be learning done on Monday and Wednesday this week, so you guys can ask those there. And yeah, otherwise, we have nothing else for you for today. Enjoy the rest of your Sunday. If you're in Baltimore, it's a nice day out. And see you in Pilot this week, and good luck on your exam.